Talk to you about today is the idea, simple idea really, of using data to understand teaching and learning. This is something that's come to be called learning analytics, the idea that we might want to use data to understand what happens in teaching and learning to make it better. I like to use this picture, which has disappeared from the center screen, to illuminate this idea of using data to understand teaching and learning. It shows the diag in the 1940s when it was still crowned by Dutch elms before the Dutch elm disease killed them off. Very cathedral-like, very beautiful, with light shining in. And that light shining in is exactly what I'm talking about. I want to shine some light on what's really happening in teaching and learning on campus, to really try and understand it, and to use data to do that. Let me give you a little bit of background. As Fred mentioned, I'm an astrophysicist, and I spent the first 25, 30 years of my career first very carefully measuring nothing. So we spent 6 years on my thesis project building an experiment which was meant to open a whole new field of astrophysics, 100 TeV gamma rays, and what we discovered is that there weren't any. But we knew it for sure, right? We were so sure that that field is still dead. All right? This is important for me because it taught me something about the nature of making measurements. It taught me the importance of not fooling yourself. Because the reason we built this experiment is that other people had claimed to see such things. And they weren't lying, but they were wrong. Right? So it instilled in me a kind of enormous amount of statistical caution, which I think still is important to my work. Then, not being happy with measuring nothing even very well, I went and decided we would try to measure everything, or sort of measure everything. I went to work on the Sloan Digital Sky Survey, whose aim was to map the universe. Right? Kind of the opposite thing. They promised that we would measure 100 million galaxies, and we knew there were galaxies out there. There was no question they were out there. So that was a nice change. It taught me another kind of work about statistical data inference, because now instead of carefully measuring nothing, which is important but boring, we had very, very rich data in which there were all kinds of things going on. And the problem there was how to sort out a really complicated thing. I've also done some work with people here at Michigan, especially Karl Akerlof, on hunting really rare things, or things that happen only briefly, like gamma ray bursts. So over the years, I worked on a lot of different kinds of observational science and on drawing inference from data. That work has been crucial for the work that I'm now doing in learning analytics. So it feels like all that career of physics was preparing me to approach the much more difficult problems of trying to understand teaching and learning. I wanted to say a few words about observational science. You know, our canonical model of science is to do experiments, to take a phenomenon into the laboratory and control all the conditions around it, watch it happen over and over again, replicate those experiments, change the parameters, right? That's a wonderful way to do science, but it is not a method which is open to every question that we might like to raise. In particular, very few questions in astrophysics are amenable to directly experimental science. Right? We don't get to do experiments creating stars and galaxies and so on. What we do instead is we watch the natural experiments that nature produces. I'll say some more about that in just a second. The other thing that's come out of all this work is that I really like to measure things. So when a data set shows up and there's an opportunity to measure something in it, I want to get it on my computer and work on it. Right? And that has been a characteristic trait of this. I've come to think of myself as a data scientist. I didn't think of myself as a data scientist before because there was no such phrase. Right? It was actually first used here on the Michigan campus in the stats department in 1998. It's an emerging field. We have data science now in a way we didn't before because data is so much more widespread and available than it was before. So this is a really big emerging thing. And I feel that I really am a data scientist. Let me say a few words about these two kinds of science, experimental science and observational science. Over the years, I've had to convince myself that it's possible to do really robust observational science, never having a controlled experiment, because it's the only way to do astrophysics. So I've come to think that the distinction between these two is not nearly as large as people like to claim. What happens in experimental science is you build something like the Large Hadron Collider. You put around a little point in that Large Hadron Collider the largest machine that humans have ever built, and you watch protons run into each other. You don't like take the proton and exactly manipulate what it's doing. You just smash them into each other and watch it. It's nice because it happens right there inside your apparatus. It's close. It's nice because it happens when you want it to happen. That's nice. But you're really still just watching nature do what nature does, just in an easier kind of environment. Now, we can't take two galaxies and collide them with one another. For one thing, it takes way too long. It'd be very boring. Take two galaxies, let them go. Right? But, of course, we can't control those conditions or anything else. But we can see the many, many different cases and ways in which the universe collides galaxies. And if we take advantage of those natural experiments, we can learn about the world. It's possible to learn very robust things from observation. I don't think people knew this in, say, the 17th century. They weren't really thinking about it because the world looks like it's full of particularities. Everything is unique that you see in the world around you. And so you might not think there's any pattern or regularity in the world that you could really work with. But there are such patterns. I use this picture from the Hubble Deep Field just to give an example of that. You look at the sky, it's just full of all kinds of stuff. There's all kinds of different galaxies. How could you say anything other than here's one particular galaxy in one particular place? Well, it turns out that if you start to examine and pay attention, patterns emerge from what you see there. They suggest that there might be some generalizable things that you could say about galaxies. And then you can use future observations to see whether those generalizable patterns really are general. You can test it by looking further. And a great example of this from cosmology is the Hubble relation. So in the 1920s, Hubble and some of his colleagues made measurements of the distances to some galaxies and also the redshifts of those galaxies, how stretched out their spectra were. And they discovered a connection between those two things, a pattern. That pattern looked like this. They found that when they measured the distance to galaxies and they measured the redshift of galaxies, the farther away a galaxy was, the more redshifted it was. That was a pattern that just emerged from observation. They then wondered, would that continue? What would happen if we asked about galaxies that are still farther away? Would they have even bigger redshifts? It's like a theoretical prediction. It comes from observation, but it's a lot like a theoretical prediction. And of course, the story since the time of Hubble has been that we have continued those kinds of measurements and continue to see, with increasing distance, increasing redshifts for galaxies, to such an extent that this original Hubble diagram fits in the little red box that's down on the corner there. So you can learn truly generalizable things about the world from observation. It doesn't just come from experiment. Now, I give this little bit of introduction because I want to talk about making measurements like this in a place where it might seem even less likely that we could learn something from measurement. And that's from observing education. I want to pause here. I don't know if this picture has the same effect on you, but when I look at this picture of the Diag, surrounded by green trees, with people walking around in shorts, it just evokes a sigh, right? Well, we all know it's coming, right? So this seems like something extremely particular. All these individual students, every class seems different and unique. What could we say about a world like that that is so particular, right? Are there stable, generalizable patterns in the education system? It's an open question. And I'm going to show you some information from our first attempts to answer it. Okay, so why are we doing this now? The real reason we're doing this now is because data is relevant data, data that's important for teaching and learning, is both increasingly accessible and increasingly extensive. I'm going to talk about two kinds of data here. One is something that we call student record data, and student record data is the data that exists about every one of you if you ever went to school or college. Right? Schools and colleges have always kept records of the grades of students, of their admission file, of how they progress through the university, and what degrees you receive. It's the stuff that's on a transcript. Nothing very new about that data. What's new about it is that you can get it all with a query to a database instead of going through hundreds of file cabinets to pull all that data out. So the accessibility is new there. The other thing that's happened is that on the right-hand side of this diagram, you can see new kinds of data that have emerged because education increasingly is mediated by technology. So students, when they work on things for classes, when they interact with one another and with teachers, they do so through technology, which can collect information about all that activity as a kind of digital exhaust. It kind of just falls out from the process. We don't have to do a lot of work to have it. So all kinds of information, not only about how students do, but about what they do, is available through these kinds of tools. So if we hope to learn what kinds of things do students have to do in order to learn, we now have a chance to observe what students do and then see what the outcomes are. So the connection between behavior and outcomes is more accessible because of this kind of data. I'm going to spend most of my time talking about the student record data, the stuff that's on the left-hand side of this, because it's the starting point for us. It's a record of all the academic information for about 100,000 students here at the University of Michigan from the time they were admitted all the way to the time when they graduated. It lets us study what's been going on in higher education, at least here at Michigan. The real future of learning analytics lies on the right-hand side, where we start to be able to see more about students. And the real goal of that kind of data is going to be to allow us to understand how actions affect learning. All right? So the student record data includes some very simple things, some socially relevant population categories like gender and income, test scores, the things that we get when students apply to come here. Test scores are kind of a point performance measure. You went in on some Saturday and performed well or poorly, and that's what shows up on the test score, right? And then we have grades. Grades are an interesting thing. A lot of people in the education community would tell you that grades do not measure learning. That seems like a pretty strong statement. And they have an argument to this. There is a way in which grades, if used naively, would be very poor measures of learning. But grades contain a lot of information. You know how much effort you put into getting the grades that you got. If you've ever been a teacher, you know how much effort teachers put into evaluating the work of students. So there's a lot of information in a grade. We just have to use it wisely. Okay. All right, so let's think a little bit about how these things we measure relate to what it is we want to know. It's essential that we should be really careful about the difference between what we measure and what we want to know. We might, for example, like to know about learning, right? Or talent, or to measure a student's future performance, or to figure out how hard they work. All of those are things we really want to know. What we measure instead are other things like grades, click streams, chat room usage, when they're doing their homework, right? They're not exactly what we want. And it's really important to keep that in mind because people often slip and say, oh, students who got A, they're talented. Well, grades are correlated with things like that, but they are not the same thing. And we have to be careful about that. All right, let's get started on talking about what's happened here. So learning analytics started with me with something called the Better Than Expected project, and this project grew out of my experience as a teacher. My experience as a teacher is illustrated by this picture. I am the blurry person in the front of the room, and to most students, that's all I am. I've taught large introductory courses for a long time, and students are satisfied when I teach these classes. They like these classes. I enjoy teaching these classes. But then, when it really gets down to it, it doesn't seem like it's going as well as I wish. You know, once in a while you ask a student a question, and they can't answer, and you think, really? How could that be, right? So it's all going smoothly, but there's this underlying sense that it's not all right, that something isn't perfect about this, okay? So in 2008, I learned that extensive accessible data about these classes exists. And I did what I do when I learn about data existing. We went and got it. So we started a project called the Better Than Expected project. And this was inspired by work that Scott Freeman did at the University of Washington in biology. He wanted to understand not only who was doing well and poorly in the class, who was getting an A or who was failing, right? He wanted to know who was doing better or worse than expected. So he wanted to account for the preparation and background of a student in assessing their performance. So if you were a student who's always gotten A's in every other class, and you get a B+ in this class, that feels like really bad performance, right? The relative performance is really important. So he came up with this idea of doing performance prediction, and we decided, oh, that's a great idea. Let's try that here at Michigan. So we got data for students who'd taken introductory physics here at Michigan, 49,000 students who had taken introductory physics here at Michigan. They sat in these chairs week after week, right? 49,000 students. And we used it to make predictions of performance and then to ask who does better and who does worse than expected and why, right? It lets us pick this apart. Okay, so we learned a variety of things. I should mention, this was a project of the physics department. Dave Gertis is here today. He was a part of this. Gus Everard, some of our students, Lori Lai, Kate Miller, and so on. We started this work in 2008, and it's still kind of building up steam. The first thing we learned is that student grades can be predicted pretty accurately, and that the way you predict them is kind of trivial. If you want to know what grade a student's going to get in their next class, ask what grades they got in their last class. Right? We kind of all know this, right? It's actually what makes grade point average a number that we care about. You know, you get about the same kind of performance across the way. If you're a 3.8 student, you're mostly getting A's and A minuses. If you're a 3.0 student, you're mostly getting B's. But it's true in the data as well. It's not just an assertion. This allows us to make predictions of grades, to see who's doing better or worse than expected, and allows us to move to these new kinds of measures. The next thing we learned is that all introductory science and math classes impose on students something we've come to call a grade penalty. Students get lower grades in these classes than they do in their other classes. No one is fainting, so I assume that this is not a huge surprise to you, but I will show you a little bit about the details of that. The second thing we learned was more of a surprise. It is that there are significant performance disparities among students who come from different demographic groups. I will talk today only about one of them, about gender performance differences, about the fact that men and women with the same preparation have different outcomes in some of these classes. And I'm going to give you some details about that. So let's start with a basic figure that is one that we have worked with a lot. It displays the relationship between students' grades in other courses and their grade in a particular course, in this case, our first semester introductory physics course. So the x-axis of this graph shows you the GPA of those students in their other classes, the grades in their other classes, and the y-axis shows you their grade in Physics 140. Stretched across the figure are a set of blue points with error bars that run sort of through the middle of the figure. Those points represent the mean and the error on the mean for students in each bin of GPA. So if you're a 3.5 student, I could go up to this point here and read off the fact that you probably receive a grade of about 3.0 in this class. On this figure, we've drawn a line, a one-to-one line, that solid line that goes up there. If students received grades in physics that were consonant with their grades in other classes, all of those blue points would lie on that line. But they don't. They all lie below that line. And this is the fact that we have come to call the grade penalty of this class. Sign up for physics, and you will get an average grade that is lower than the grades you've received in your other classes. Your GPA is going down. Again, it's not a total surprise to any of us, but we can measure it now. And if we average that over all the students in the class, that grade penalty for the class is about 0.4 letter grades. Fairly substantial. Students feel that kind of difference. Okay? That's the first fact that we discovered. Let me show you something about gender performance difference. So I'm going to show you the same figure, but now with points generated for male students, the lighter colored points that are on the top with smaller error bars, and points generated for female students, the darker colored points that are a little below that. There's a substantial difference in the grade penalty paid by male and female students in these classes. For male students, it's about 0.32, and for female students, it's about 0.59. Quite substantial difference. Remember, in this case, we're accounting for their performance in other classes. So we're taking people who in their other classes have performed the same way and asking how do they do here. So it's not like a gross comparison of male versus female. It's much more refined than that. You might ask, is it GPA differences that create this? And if you look here, I show the average GPA for male and female, 3.10 for male and 3.14 for female. So female students come in with slightly higher GPAs, but very slightly. And then the grades are shown here too. The average male grade, 2.78. The average female grade, 2.55. So the difference is mostly in grade, not in GPA. Okay? We're going to talk some more about this. Is this gender performance difference real, or is it some kind of statistical fluke? So this is the kind of thing that training as a data scientist makes you want to do, is pick this apart. Now, I've already included error bars on this that, if I've done them right, would convince you this is really a statistically significant difference. But there's all kinds of other games you can play that I would play as a scientist to convince myself that I'm right. One of these games would be to go back to the data and say, all right, what I did in the first figure that's shown up here on the left is I separated the students into a group of female students and a group of male students. Those two groups had a certain number of people in them. And I noticed a big difference. What if I was to separate all the students in the class into groups of the same size as the group of females, same size as the group of males, but do that at random? Right? If this was a random fluctuation, then I ought to often see a random selection like that give the same kind of result, right? Simple test, a sanity test, we would call it. So if you do this, it looks like that, right? The error bars that are on this figure are accurate. It's measured at enormous significance, this difference. It's not an accident, a statistical fluke. You could ask other kinds of questions. Does it always happen? Or is it only happening sometimes? So what this figure shows is two sets of points for each term going back into 2007. There are some blue points that start with a square on the top and an arrow pointing down. The square on the top shows the GPA of male students coming into that class, and the end of the arrow shows the grade they got in physics. See what I mean? So we're looking at both things, grade and GPA. And the red one with the diamond on the top shows the female GPA coming into the class and the female grade going out of the class. And you can look term by term and see that most of the time, female students come in with a little bit higher GPA than male students, and all of the time they go out with grades that are lower than male students. That's saying the same thing. There is this grade penalty, and it actually is visible, measurable term by term. What I showed you before was aggregated over all those terms, right? So you can see it more clearly. But even term by term, you can see it. So that's a question to ask. Another kind of question people always ask is, could it be something else? Maybe there's something hiding in here, something that would predict this difference between male and female. So we take everything we know about the students and throw them into models which attempt to explain this difference. And ask then, do we still need to know the gender of the student to see the difference? And we do. So we can do multiple linear regression like this, and just to show you something from this, the multiple linear regression shows that GPA is by far the strongest way of predicting their grade. These numbers sort of reflect that. By far the strongest way of predicting their grade. The next highest thing is gender, and the third highest thing is ACT math score. Okay? So we don't have an explanation from the data that we have of why this difference exists. We've also done more sophisticated analyses where you very carefully match male and female students in the whole parameter space that we have, and these differences are robust, they're real. So this raised all kinds of questions. Is this just a problem for physics, or does it affect other disciplines as well? Remember, we didn't know about this in physics because we hadn't looked. Nobody knows about it in other classes because they haven't looked, right? If it is in other disciplines, which ones are there? And is it something about the disciplines? Or is it something about the way the classes are run? What's causing this, right? We have a lot of data to address those questions. Once we see what's happening at Michigan, you might ask, is it just at Michigan? Or is it a generalizable thing that might be true about the larger higher education system, about the way we teach physics across the country, or the way we teach across the country? Are these patterns seen on many campuses? Which ones? Why? All these kinds of questions. Okay. Since that time, we've been working on answering those questions. In 2011, I got together with a professor from the School of Information named Stephanie Teasley, and we started a lecture series. Because if you want to figure things out in academia, you talk to each other about it. Right? So we started something called SLAM, the Symposium on Learning Analytics at Michigan. It has since gone on ever since then. You can find all the talks online if you're ever interested in these kind of questions. Feel free to search for SLAM at the University of Michigan and you'll find it. Those conversations led to the university picking up this question. So the provost of the university at the time, Phil Hanlon, was a mathematician. He totally understood this approach. It made sense to him. We should use data to understand teaching and learning. and he charged a group of faculty members with trying to optimize the information environment at the University of Michigan for this. This has led to 3 years of very active work here on the Michigan campus, and I'm happy to say that Michigan is now playing a leadership role in this kind of work nationwide. So I got a note from a colleague at Stanford University, you know, Innovation Central, right? The other day, telling me about something they'd recently done, which, as he put it, had them catching up to Michigan. So we like to hear that. We like to hear that. We want to get that message out. Now, there is an objection to analytics that is often raised, and often when it's raised, this quote is put on the board. Not everything that counts can be counted, and not everything that can be counted counts. So why do you suppose Einstein is evoked in this epigrammatic way all the time? Why is it if you have a quote, ooh, you hope it comes from Einstein? Right? Because if it came from Einstein, people would believe it, right? He's a genius. Actually, this quote doesn't come from Einstein. Right? It actually comes from a book written in 1963 after Einstein was dead. And it said, it would be nice if all the data which sociologists require could be enumerated, because we could then run them through IBM machines and draw charts as the economists do, or perhaps the physicists. However, not everything that can be counted counts, and not everything that counts can be counted. All right? So people ascribe this to Einstein because they want it to be true. But that's really an assertion. All right? So my belief is that everything that's real can be measured. In fact, the idea that when you observe a thing, the only way you can observe a thing is for it to interact in some way with the world. Right? And when it interacts with the world, you can measure that. Even seeing it, noticing it. That's a measurement. And if it never leaves any trace at all, something which never interacts with the world, that's like my definition of something that isn't real. Now, I put a proviso there. I'm really not a philosopher. I don't have a license or anything like that. But I have measured an awful lot of things, and some of them are pretty weird, like dark matter and dark energy. And they're real. I believe they're real because I can see them. I can measure their effect, right? So I really believe this is true. I do concur that measuring many things is very hard, and that you won't just jump right to quantitative methods for measuring things. Often you begin, always really, you begin with observations of complicated things. You record them in language, in qualitative research, to start, till you start to figure them out. But there comes a point where you can pull parts of that into quantitative research. All right? So I object to the idea that there are real things out there that are impossible to measure. I don't believe in that. But I acknowledge that it's difficult to measure some things. There's another objection to making analytics measurements in education, which is the idea that everything is contingent and nothing is generalizable. This is what I would call the clinical objection. It used to be raised by doctors. Oh, the only way to diagnose your disease is for you to come to me as an expert, and I will examine you and tell you what disease you have. As scientific medicine emerged, partly here at the University of Michigan in the late 19th century, we came to understand that diagnosis could be done much more reliably by making measurements than by having expert doctors assess your condition. It's a great example because there still is a huge role for the clinician, right? It's not like you can just write a formula for making measurements and settle every question. The experience and subtle connections that a clinician form are often life-saving. But at the same time, you really want to know whether you have a bacterial infection or a virus, right? And they can't tell that by looking at you. Okay. So this claim is often made. It's often made in education research, and I view this as a testable claim. If I can make a measurement in different circumstances and see that the same thing occurs, then it is generalizable. You can't insist that it's not, right? You can show that it's generalizable. And that's part of what we're trying to do in our education work right now. I'm going to finish up by telling you 3 stories that are meant to illuminate the landscape of this learning analytics and to give you some sense of what might be possible in doing this work. So 3 different analyses. The first one has to do with the gender performance differences. So I promised I would tell you more about that. We use GPA to predict grades in this case because it's the strongest predictor, and it's because the way people think about themselves as a student is kind of wrapped up in GPA. So I know that some of you haven't gone to college yet. Some of you went to college a long time ago. Any of you who went through college, do you remember your GPA? I think most people do. I think most people do. So that's what I mean. It's kind of salient. So what I'm going to show you are charts that show grade penalty for all students, measured across all students, and then the gendered performance difference, which is the grade penalty for male students minus the grade penalty for female students. And we're going to explore a little bit the pattern of performance across courses at Michigan. Okay, so first let's look at another kind of class, Econ 101. Maybe some of you took this class too. Another class that has a grade penalty, about the same as physics, about 0.4 letter grades. It also has a substantial gender performance difference. 0.26 letter grades for male students, 0.57 letter grades for female students. Nobody knew this before we looked. Engineering 100. This is a STEM class, a science and technology class that engineering students take during their first year on campus. It is a project-based engineering class. So they come in the beginning of the term, and the idea is for them to learn what is it to be an engineer. So they pick up a project, they do a design. They think about the marketing of it. They make presentations about it. They work like an engineer, right? That class is evaluated by examining that work they do. A very authentic kind of work. You know, it's the kind of work you do in your real life. You get given a task, you work on it really hard, you continue to work on it until you're happy with the result that you made, and then you give it to someone, right? Evaluation in Econ 101 is kind of the opposite of that. You got 90 minutes, here's a test. Show us what you know. Really different, okay? This class, female students do better than male students. Right? English 125, first year writing, one of the biggest classes on campus. What do you think? Female students do better than male students. That's actually true on average across the campus. In most classes, female students do slightly better than male students. In a handful of classes, male students do much better than female students. Okay? Let me show you that pattern in more detail. This is a figure now that shows on the x-axis the course's grade penalty. So a course that's on the right-hand side of this figure gives out low average grades to everyone. A course that's on the left-hand side of the figure gives out high average grades to everyone. That's the x-axis. The y-axis reflects the difference between male and female grade penalty. So a course that's on the top is a course where female students perform better. A course on the bottom is a course where male students perform better. When I looked at this figure, I saw immediately two big groups of things. There's a whole bunch of classes that cluster around 0, 0. They kind of have to be, right? Everything is referenced to other classes, so there have to be average classes. And then there's a big group of classes on the lower right-hand side that includes every introductory science, technology, and math class that is a lecture course. So physics 1 and 2, chemistry 1, 2, and 3, biology 1 and 2, math 1 and 2, and Econ 1 and 2. All right? We didn't know this until about a year ago when we looked for the first time. All right? Now, just to break that out and just talk about the science classes, because you might think maybe it's disciplinary. The lecture courses all live down there in the lower right. The lab classes all live up there around the middle. So it's a pattern, right? You look at data, you find patterns, and then you start to think about what it might be. And I'm thinking about what it might be. So one thing I'll tell you is that we're now working with colleagues from across the Big Ten. And we have confirmed that this kind of pattern, this difference between STEM lecture and lab classes, is present on other Big Ten campuses as well. I find that totally unsurprising. How could it be only here at Michigan? I mean, we don't do things that are that different here at Michigan. We never got together and said, let's make sure the women don't do very well in lecture classes. I mean, we didn't do that. So it has to be generalizable. And this work is testing that idea that there might be something going on that is less about local and more about the global system of the way we do these things. Okay, so what's going on here? I think that list of anomalous courses spans many different topics. Some of them are very mathematical, but not all. For example, intro bio, the way you study for intro bio is to make a whole bunch of flashcards and memorize a ton of things, right? It's not the same. So it isn't just mathematical nature. What I think they share is that they are evaluated predominantly by timed exams. Often those exams are kind of mechanical, multiple choice kinds of exams. And that testing environment is a performance environment, which is quite unusual, right? Most of our performance in life isn't like that. So I wonder whether changing that evaluative style could change that performance pattern. It turns out there are a bunch of people who've been studying this kind of thing over the last 20 years. That work started in the early 1990s when a social psychologist named Claude Steele began exploring exactly this, gendered performance differences in introductory math classes here at Michigan. He was in the psych department here. He's since gone on and been at several different universities. He's now the dean of the College of Education at Stanford University. In 1995, Steele and Aronson published a paper which launched a world of research into the influence of environment on performance. Basically saying if we put you in different kinds of environments, how well do you perform? Right? You would like to make a measure of how well somebody really can perform, but if you put them in different kinds of environments, you get different performance measures. It's not a miracle. All right? But they began to pick this apart. They did work on a subject which has come to be called stereotype threat. And the idea of stereotype threat is a pretty simple one, and I think we all have experienced something like it. If you are in a circumstance where you have a well-founded fear that you might confirm a negative stereotype that someone has of a group that you belong to, it's harder for you to perform well. So let me try and put this in context for you. Some of the people here are very young. So if you're very young and you get put in a room full of adults, it's hard to talk to those adults and do as well as you could because you know they're thinking you're just a youth. And for the older people who are in the audience, imagine that we take you to the doctor's office and give you a memory test. Pretty threatening, right? Because you know that you might confirm what people expect, that you're not going to be very good at this, right? And that might make you perform just a little bit worse. It's not like you fall apart. Nobody does. But you do maybe 10% worse. And that's what this field of stereotype threat research has shown. I've got two pictures up there. One is the beginning of a sprint, and there is one person in that group who probably knows that most of the people in the audience do not expect him to win the race. All right? The second picture is from the Solvay conference in 1927, a very famous gathering of physicists. You can see Einstein sitting in the center. If you're familiar with old photographs of physicists, you would recognize many of these people, including Marie Curie, who is sitting here just to the right of Einstein. I'm pretty sure that every time Marie Curie spoke at that meeting, she thought for a moment before she opened her mouth about whether what she said would be interpreted as the words of a scientist or as the words of the only woman in the room. And this probably made her just a little bit less articulate. She held her own, she did fine, right? But it's a ding on performance. So Steele and others have done a lot of work on this, and he wrote a really great book in 2010 called Whistling Vivaldi that summarizes both the work and how they came to believe it's really true. It's kind of a nice book about social science, about how you learn something true in social science. So if you're interested, I would pursue that. So the way I think about this now is that it seems to me the evidence we have about gender performance differences in these lecture classes implies that we have created an environment in which not every one of our students can show us their best. Right? I want to see the very best that every student has. So I want to somehow create an environment which allows them, like athletes at Michigan, to set world records. Right? That doesn't get in their way. And I think this is evidence that we're getting in their way. Okay, that's the first story. A second story, in addition to learning things from data, it's also possible to put data to use, to take advantage of what you know and actually act on it. And the most exciting parts of this are when we will act on it in real time so that we can help a student right where they are at every moment. There are a lot of early versions of this that came out. At Purdue, they built something called the Purdue Signals Project, which would look at the performance of every student in their classes in real time and put up a traffic signal. Red light, green light, right? Kind of crude, but it was an attempt to do this. Most of the early tools aimed to catch failure before it occurs. And of course we want to do that. Failure is a really big issue if it happens to a student. But we actually want to work with every student. It's not enough to just catch failure and pull people over the line. I actually want to go to the very best student in the class and improve their class. Make them do better than they would do if we didn't interact with them. Everybody should be influenced. So that's the hope of this kind of learning analytics-driven intervention. So let me tell you about one that we've worked on here at Michigan. The problem we aim to address is that our education model is built on Henry Ford's model, kind of an assembly line system. We bring all those students here into this room. We give them all exactly the same class. They hear the same lecture. They get the same homework. They do it at the same pace. They take the same test. If we do that really well, it's pretty good for the median student, but it bores the strongest student, and it leaves the weakest student behind. So ideally, we would like to be able to, personalize it. So we've worked on that. If we could speak to every student as an individual with this kind of knowledge of their background and their goals and their current state, we would be able to personalize education and I think consequently make it more effective because we'd be working with each person where they are, right? So we have built a system here at Michigan that tailors our interactions with students, that lets us speak individually to every student, and it's called eCoach. Let me tell you a little bit about how it works. First of all, the eCoach system was built here at Michigan because people in our School of Public Health had already done it. Public health faces the same issue, right? They want to be able to speak to every individual, knowing all about them with an expert voice, but they can't afford that doctor time. So they invented computer-tailored communication systems, and they started so long ago that their first versions were printed brochures. So instead of getting the generic smoking brochure, you got your smoking brochure, right, that was printed for you. Of course, the internet came along and made their job a lot easier. So they have built in the School of Public Health something called the Michigan Tailoring System. Tens of millions of dollars have been spent building this communication system that allow you to create content, messages, things you want to say, designed specifically for an individual based on data about that individual, right? Now, this software has no idea what to say. It's just software. It's not an expert. So we need to put experts into it. So in order to build a system like this, we have to start by gathering expertise that comes from people who know about what you have to do to be successful in this class. We started, when we did this, by interviewing a bunch of instructors with something like 150 years of collective experience in teaching introductory physics courses. We went to them and said, if you had a student like this come to you with this kind of background in this certain circumstance, what would you say? And what about this student over here who's different from that? And it wasn't that helpful. Because the physics professors gave the first order answer to everything. They said you should work harder. And it is the right first order answer. Averaged over everyone, that's probably the right answer to give. But it isn't responsive to the individual. So the way we got more information about what different individuals should do was to ask students. So each student who goes through a class has an experience and learns some things about how to be successful in that class. They only learn about their own circumstances. But when you put a whole bunch of students together, you can learn about kind of the whole landscape, right? So we went and interviewed students who did better and worse than expected in previous years. And we asked them, what did you do in class? The people who did better than expected all spoke about changing their practice in class, doing something they hadn't done before in the middle of the class. And that's what led them to end up better than expected. It changed their outcome. Students who did worse than expected all spoke about giving up at some point. They tried hard, did badly on the first test. They tried harder, did badly on the second test. And then they faced a terrible choice. Do I keep trying and fail? Or do I step back and say, no, this is not my thing? Right? So you fail, but you know why? Because I just didn't really try. It's much harder to fail when you really try. So they would give up, and then the bottom would fall out. So we learned all these great things from them and tried to build it into the system. Once you decide what you would like to say to different kinds of people, you have to flow in data about all of those students and their current status, and then this tailoring system creates individually personalized messages. And they aren't magic. We tell it what to say, right? But it allows us to say to every student what we would like to say to every student, but don't have time and ability to do. Okay. This is expert electronic coaching. That's why we call it eCoach. And what happens is there's a website that gets updated regularly for the student. It gives them information about how to start the class, what's a good way to get started. A week before the exam, it tells them how to get ready for the exam. After the exam, it reviews their performance and says, here's how you did and what you should think about for the next exam. It coaches them through the class. That's the idea. And the expertise came from a whole bunch of places, like I was telling you about. One more thing to mention about expertise. Our goal in doing this, really, in fact, the goal of teaching in many ways, is to change people's behavior. Students don't learn ever because I make them learn or I do the learning for them, right? Students learn when they do something. So if I want students to be better students than they are when they arrive the first day, I have to change their behavior. They have to do something different, right? So in doing this work, we consulted behavior change experts, people whose research is about how do you change people's behavior. And they taught us many interesting things. One of them is that if you're going to give a behavior change message to someone, it doesn't only matter what you say, it matters who says it. So when Professor McKay says, you have to study 5 days a week for this class, the student says, no, I don't. Right? But if that student's roommate says, you have to study 5 days a week for this class, then the student thinks, oh, maybe I do. Right? Because of the identity salience of the messenger. If it's a person like you, who you really believe understands your circumstances, you're much more likely to take their advice. Right? So when we present advice in this system, we give it in the form of testimonials that come from identity salient peers. So you're a certain kind of student, you're a pre-med student, you're terrified of physics. We give you advice from a person who starts off by saying, I was a pre-med student, I was terrified by physics, but I learned that if I did X, Y, and Z, I could do pretty well in this class. Right? Same message I would give, but given in a different voice. Okay, what does this look like? Well, it makes these nice personalized web pages, and I know you can't really read it very well, but here's one of those testimonials with a real Michigan student on there. Of course, we ask their permission to do this. They're happy to do it, and so on. We give them things that show them where they stand in the class. How did I do on exam 1? They get figures that look like this. We give them grade predictions, and because this particular one comes from a statistics class, they've actually given the students not just a predicted grade, but a probability distribution function for their predicted grade. Right? Statistics. And they tell them all about how they did it. To make our prediction, we used the same grades you have so far this semester. We could have just done a regression model, but instead we did random forest regression. And if you want to learn about that, go read about it, right? So it's got an extra teaching tool that you can build into this. And it's, it works because it's salient. Every student wants to know what is that distribution for them, not for the whole class. They want to know it for them, right? Personalized. So in fall 2013, we expanded this, and over the last couple of years, we've offered it to about 5,000 students in these courses. I don't know whether this system or our approach will be a central part of education in the future, but I am certain that personalization will be. Right? Systems will be used to personalize education more deeply, and it will help. All right? We're working to expand eCoach right now. We're building this thing called the Digital Innovation Greenhouse, which is a kind of ed tech accelerator. And if anyone here in the room is a programmer and looking for a job, please apply, because we have 4 jobs on the University of Michigan jobs list right now to work on projects like this. So we've tested the impact of this. I'll just tell you about it for a second. We put people into 4 user groups: non-users, people who never really looked at the system; low users, medium users, and high users. In order to form expectations for performance in the class, we look at the non-users. We look at how their grades depend on their GPA. We use them as the prediction, and then we compare people's performance to that prediction. So we make this better than expected score, which is how well did each group do compared to the non-user group, accounting for the GPA of those students. Okay? When we do that, the results we get look like this. This is sort of just preliminary stuff. The non-users, of course, perform exactly as expected, so they lie right along the 0 line here because we set up the expectation based on them. Low users show no real change. Medium users and high users, though, do show changes, improvements in performance. I don't think this is at all proof that this is a causal impact, that this system made this happen, but I think it's happy news. We would certainly feel worse if this was not the case. Teasing out causal impact requires using more subtle techniques like random controlled trials and things like that. So some of that's going on now, but it's just a first indication of whether it works. Okay, I'm going to finish with one last thing, which goes back to this GPA. This is a project I'm doing right now with a couple of former Michigan students, William Murdoch and Jamie Fogel. It involves rethinking GPA. I think we have to rethink GPA for a couple of reasons. First, we use it very heavily. So here at Michigan, for example, distinctions and other honors are awarded based on tiny differences in GPA, down to the 1,000th place, right? So we're really relying on this number. At the same time that we're relying on this number, any thinking tells us that a simple average of grades can't be the best estimator of performance. We know this because there are variations in grading philosophy from one department to another, which are fine, right? There are good reasons to give out grades in different kinds of ways. I think that's okay. The bad thing is then to average them together as if they were the same. That's the mistake. There are variations in course difficulty. Some courses are super hard. You work like crazy, and some courses are easy. There are also variations in the student group that takes a class. Sometimes you take a class with a bunch of really hardworking, great students, and other times you take a class with a bunch of people who are dialing it in, right? So we would like to use the existing data to make more subtle measures of performance. I say we want to use the existing data. The only alternative is to insist that everyone give out the same average grade. This has been tried in higher ed for 100 years. No one has ever had any success in doing this. It's probably the wrong approach because there really are different reasons to give out different kinds of grades. Okay? So let's use the grades as they're given. First, let me motivate the fact that we really need to do this. Here is a figure that on the x-axis shows the average grade given out to students in courses in each subject. The y-axis, just to spread it out, is actually the standard deviation of the amount that grades vary in those subjects from course to course. All right? So you can see, first of all, that there's about a 25% variation in the mean grade given by department. Okay? If you're examining this figure, you might look on the lower right there and see a department that gives out almost all A's. ENS. Does anybody know what that is? It's ensembles. It's marching band. It's okay. They probably should give out A's. But given that they do give out A's, we probably shouldn't average those together in exactly the same way we average other grades. I mean, it's fine that they do, but just to ignore that fact might be a mistake. On the other side, over on the left, you can find the math department. Not a big surprise. Econ, materials science, biology, chem, physics is in here somewhere. Statistics. I like the fact that statistics has a really small dispersion among their classes. I think it's because they pay more attention, maybe, than other departments do. Anyway, all kinds of fascinating things, right? In doing this work, we went to try and understand the history of grading and found this wonderful paper written in 1908 by Max Meyer in Science, the journal Science. In it, he says, the experiment started by the faculty 5 years ago must be pronounced a complete failure. That experiment was grades. And both students and faculty have, before now, felt it to be a failure. There is no uniformity of grading, but the greatest divergence. It has come to be admitted openly that a student who is anxious to win honors must be careful to elect his work under certain teachers and avoid others as much as possible. So this is not news. In fact, Meyer has in that paper a whole table of the average grades given out in all these classes at the University of Missouri where he was working at the time. And I tell you, the chemistry department there was brutal. In that 5-year period, they gave out 1% A's. 1%. 5 years. Okay? Our chemistry department is not that brutal. Okay, so we have a problem. What might we do about it? Well, one simple thing that we might do about it, I'll just put an equation here, but I'll explain what it means, is to acknowledge that the average grade in classes is different. And so what we might do is compare your grade to the average grade in the class, instead of comparing your grade to every other grade that's ever been given. This was actually inspired by a baseball statistic called wins above replacement. And the idea of wins above replacement is that if you play for the Yankees, you're going to win a lot of games, right? But it's not your fault, right? It's because the Yankees are good. So we should account for that in assessing a player's performance. Same thing here. If you take a class that gives out low average grades, we should account for that. So the simple way of doing it is to take a number, which is your grade minus the average grade, and average that number instead of averaging your grade. So if you do better than average, those are positive numbers. If you do worse than average, those are negative numbers. All centered around 0. Okay? Now, you might wonder what happens when you do this. So I'm going to try and give some first indication of that. What each of these 9 figures are is a set of distributions of this grades above replacement score, a score that's good when it's positive and weaker when it's negative, the distribution for a set of students who have the same GPA. So I want to compare how GPA compares to this grades above replacement thing, right? And what you find when you do that is that low GPA students are mostly worse than average. They're mostly on the negative side. You can see that on the upper left-hand panel there, all right? But some of them, even though their GPA is low, are really kind of average students because they took classes that give out a lot of low grades, all right? So we can account for that. Students who are mean GPA students are mostly right around average, and you can see this number then scatters right around 0. But some of them are actually much better than they look, and some of them are not as good as they look, right? And right up at the top, high GPA students, these are students with a GPA of 3.61, right around 3.6. Those students are mostly above average, some are much above average, and some are actually kind of average. Okay? So it corrects for, it allows us to improve the measure of performance that we have. Okay? This same method, though, has a drawback. It assumes that all the students in every class are the same. And we can actually show that they're not. Students who are strong students who have high GPAs are more likely to take difficult classes that give low grades. So by comparing you to the students who are in your classes, we're still selling people a little bit short. So ideally, we would account for that fact as well. And we have done that. So we have a better method. And this is a method, let me try to explain what it is. It says that the grade every student receives in every class, the grade that the student gets in a class, is built of two pieces. A part of it comes from the student, the quality of you as a student. Something like your GPA. It's a number that reflects how good a student you are. And the other part comes from the course. What kind of average grade does this course give out? All right? And what this model does is it takes all the grades every student has received in every course. This is a very large matrix, several 100,000 by several thousand matrix in order to estimate these parameters. So we had to use a little supercomputer to do it, but you can, it's not that hard. And it allows you to get a new estimator. This is the thing that would replace GPA, or grades above replacement, for every student. It also allows you to measure this course term effect. Was the instructor likely justified in giving out high grades? Because if all the students in this class were great, give them A's. Right? Or if all the students are really weak, they should all get C's. Right? So it allows you to measure whether the instructor got it right when they gave out high or low grades. Kind of interesting. I just one thing to show you from this. This is a figure that shows the mean grade in the course and the course effect, that number that comes from the model. And what it shows you is that when courses give mean grades that are low, the low grades are mostly due to the course. That's what's labeled in the lower left-hand corner here. And when a course gives out high grades, the high grades are mostly due to the course, not mostly due to the students. But there are times when an instructor gives out an A to everybody, and they really should have. Right? It can happen. Why not? You get a bunch of really great students, they definitely deserve A's. Same thing down here. It can happen sometimes that you really should have given C's to all those students. Right? But most of the time, the average grade is really the influence of the course. Okay? So that's a third example of ways in which what we hope to do is to improve the way we measure what students are doing. This is a performance measure. I'll just mention that we're hoping to make a measure of the richness of a student's experience. Something that's kind of perpendicular to performance. So if you're a student who goes out and takes all kinds of crazy classes, we want to recognize that and give you credit for it in a way that seems as important as GPA. And if we could do that, I think that would encourage students to have a better education. Maybe we end up with 5 or 6 different things, all of which reflect the student's experience better. Okay? All right, I'm going to finish by saying just a couple words about data and the future of education. So we have tools now that can expose this information to everyone on campus, and the real goal is that everyone should be able to learn from the experience of everyone else. All these people have been through here. There's all kinds of information about how to go through here and what works and what doesn't. Everyone should be able to learn from that. We're also working to explore and represent what students and faculty do in richer, better, more accurate ways, getting closer to what we care about. Can we turn these things into measures of learning, of the impact of individual teachers? If we could do that, it would help us to improve what we do. We hope that everyone on campus will expect teaching and learning to be evidence-based, so that they would go into the class doing things, making choices about how to run the class because of evidence, not just because of tradition. Right? They would learn how to do a better job. The University of Michigan, one of the things this has convinced me of is that the University of Michigan is a fantastic laboratory of education. We educate thousands of students here every term. We have them instrumented. We're measuring all kinds of things about them. We should use it as a lab. We should try new things and see if they work. And if they do, we should advertise them. Right? It's what we do. And what I hope is that both students and faculty will better understand what's going on. And I'm really pleased that the way this transformation is happening is through, this data science thing, which has been emerging in a bunch of different places. The idea that you could take data like this, and if you have the right kind of sensible approach to it, you can learn real generalizable things from it. And I hope we'll see that happen kind of all across society as time goes forward. Thank you very much.